very tenuous. So it'll be on the 15th as advertised last week, which is Thursday, not this Thursday, obviously a week from Thursday. And it will be on chapters, make sure I get this right so I don't lie to you. So it'll be chapters 5, 6, and 7. So that's root finding, optimization, and then numerical integration, which is what we're covering now, which corresponds to problem sets. Let's see, that would be 4, 5, and 6. So you've turned in 5, and 6 would be based on numerical integration. There will be an equation sheet as there was for the first exam. That'll be up on Blackboard. I need to make a few changes to it, so it's not there yet. And format, options, logistics will all be the same as they were for the first exam. Okay, any questions about that? So we'll finish up the material today for that exam. So you have time to finish your problem set 6, turn it in, get it graded. We'll start new stuff on Tuesday that will not be on the exam. Finally, I have a very important announcement to make. Every year, they track how many people are using programming using various languages. And it's always a very interesting list. So you can obviously see trends. So over the last number of years, you could see Python kind of moving up. I think Python's now number 2, if I remember right. One of the versions of C, one of the C's is number 1. Surprisingly, Pascal is still there. I don't know why. I don't know who still programs in Pascal. That was like the 1980s. I don't know, maybe some old geezers who never caught up. But guess what's back on the top 20 list? Fortran. My beloved Fortran. It's coming back. It never dies. So I've said it from the very beginning, there's still a lot of good reasons to use Fortran in certain circumstances. A lot of people are not programming in Fortran per se, but there is a lot of really good Fortran code out there. They call it legacy code that's been around for many years. It's been debugged ad nauseum. It's been used all over the place. It's extremely efficient. Most of these algorithms are the fastest possible, or at least available. Many of the libraries, numerical libraries that we use, so for example, in Python and MATLAB, they both use LAPACK and BLAS. And all of those routines, which you can't actually see, but are available to you to use, those are all written in Fortran. So there's in my field of study, CFD, computational fluid dynamics, a lot of the codes were originally written in Fortran. Now, the modern version, they hide, of course, the Fortran from you, and it's the front end is, you know, C or Python or something else, Java even, but the underlying solvers and the underlying code is still, much of it is in Fortran. But according to this ranking, there's quite a bit of renewed interest in Fortran. What is the day of the exam? 15th. Oh, I love it when you guys answer your own. Well, the post, yeah, no sample exam. You have 2 sample exams now in terms of knowing what to expect. I came in slightly late. Can someone give me, yep. Yep, good. You guys are helping each other out, great. Okay, anyway, so there you go, Fortran. Any questions about anything before I get rolling? So as I said, if you haven't picked up your exam, if you took it in person, I have them here. You can come get them now or later. But in the meantime, we're going to continue with numerical integration. So we've discussed the Newton-Cotes formulas. So trapezoid method, Simpson's 1/3 rule, there's a Simpson's 3/8 rule, and there's others. The idea with these is if you have a set of points, data points, and you want to integrate from, say, A to B, the easiest way was to simply take a rectangle corresponding to each of these points and add up the areas of those little rectangles. Super simple, couldn't be easier. A step up from that was the trapezoid rule, where we said rather than just making these rectangles, why not make these trapezoids like this? Obviously that would be better because it's going to be closer to the actual function. So that's the trapezoid rule. Then the Simpson 1/3 rule is saying rather than using straight lines between each point in order to give us a trapezoid, we could use a parabola across 3 points or 2 intervals. And that should be even more accurate. So that's the basic idea behind these Newton-Cotes integration formulas. Very simple conceptually, very intuitive, just adding up the little slivers, the areas under the curve, and it's just a matter of how accurate do you want the function, the approximating function to be as compared to the actual function, which of course we don't know because we only know these data points. So now we're going to look at Gauss Quadrature. I did introduce this last time. And the idea is instead of having fixed points and then integrating, approximating the integral under the curve based on those fixed points, in some cases, namely in certain finite element methods, well, all finite element methods and certain other numerical methods, we actually know the function itself. We have a f of x function, and we want to integrate it approximately, but in a very, very efficient way, because we're going to do it a whole bunch of times in the context of this numerical method, such as finite element methods. There are 2 basic approaches. We're going to take a look at Gauss Quadrature. It's the most, by far, the most popular. And the idea is you recognize that now we can move our integration points, the xi points, wherever we want. I'm not limited to the values of xi where I have the data. I can put them wherever I want. So I'm going to put them in a place that gives me the most accurate approximation of the integral under the curve, the area under the curve, as possible. Those points are called Gauss points, and we can determine what they are. I'll show you how we calculate them in a minute. So here's the basic idea. So we went over this last time, but here's the trapezoid rule. Here's the actual function. And I draw a trapezoid, straight line between the points, and get the area under the curve. Obviously, I'm missing all of this area. So that's the inaccuracy, that's the error. In using these Gauss points, so Gauss Quadrature, I have the same function, but now I can move these points wherever I want. So I could still say, well, let's just draw a straight line between the points. But now I could pick the location of the points so that this area here and here exactly balances with that area, cancels it out. So now it's more accurate. Now, again, I can only do this if I know the function, if I know f of x. So this is a very different philosophical approach than what we did before, where we had the data points and we wanted to approximate the area under the curve. So what I'm going to do first is rederive it. So I'm not going to consider, I'm going to actually rederive. So I'm going to rederive the trapezoid rule to kind of give us a clue as to how this approach works. So we already know what the trapezoid rule does. We know the end result. We'll get the same result in the end. But what I want to show you is another way to get it. And this will segue into the Gauss Quadrature approach. So I have my f of xi and f of xi plus 1. So the 2 points, neighboring points. I can get the value of the area under the curve between those 2 points, so for that one sliver, by integrating f of x from xi to xi plus 1. So just across the width of that little sliver. Now I'm going to express that approximation in a slightly different way. And this is the way that we'll do it for Gauss Quadrature. So that's why I'm doing it this way, so we can see, kind of get a feel for how this approach works. So I'm going to have a constant C0 times the value of f at xi plus C1 times the value of f at xi plus 1. So at this stage, I know f of xi, and I know f of xi plus 1. So I just need to determine what the C0 and C1 values are. If I know those, I can get an estimate for the integral of that sliver, and then, of course, just add them up. Well, how can we do that? Well, I have two constants, C0 and C1, so I need two equations for those two constants in order to solve for them. So let's say, for example, let's assume that f of x is a constant, just equal to 1. And I'll go through the steps, but what we'll get is an expression for xi plus 1 minus xi in terms of these constants that I'm looking for. And then I'll come back and actually do it. And then I'm going to do the same thing, but where f of x is equal to x. I'll do the integration, and I'll come up with another expression, another equation for C0 and C1. So that's going to be two equations for my two unknowns. If I can solve them, then I know what the C0, C1 are. I can put them in here, 7.4, and I have an approximation for this integral. So that's the basic path we're going to take. So again, I know the f of x now. I'll do the integration and figure out where the Gauss points should be. Okay, so if f of x is 1, then the integral of 1, of course, is just x. Put in the limits of integration. That's xi plus 1 minus xi. Well, that's super simple. On the right-hand side, I have C0 times f of xi plus C1 times f of xi plus 1. But now f of xi, well, that's just 1, because all f of x's are 1. F of xi plus 1 is also 1. All right, so I have xi plus 1 minus xi is equal to C0 plus C1. So that's one equation for my two unknown constants, C0 and C1. Again, I know these, and I know these. Okay, we do it again for another known function. F of x is equal to x. So integrate x with respect to x. That's 1/2 x squared. Put in the limits of integration. I have a half x I plus 1 squared minus x of I squared. And on the right-hand side, I have C0 times my f of xi plus C1 times f of xi plus 1, just like before. Now, f of xi, well, that's xi, because f of x is just x. So I'm doing these function evaluations. F of xi plus 1 now is just is just xi plus 1. So now I have this as my second equation for C0 and C1. So two equations for two unknowns. Now you'll notice this one's nonlinear. So it's two, in general, nonlinear equations for my two unknowns. If I solve those, there's only two, so you can just do some algebra and you can get the solution. I won't bother, because we actually don't care about this case. I'm just recreating what we already have, the solution we already have. But if I solve those, I can get that C0 and C1 have to be the same, and they're equal to 1/2 times xi plus 1 minus xi. So basically the average between the two values of x. Well, if C0 and C1 are the average of those, when I put them back into C4, look what I get. The integral of my little sliver, f of x, from xi to xi plus 1, is the width of my sliver, xi plus 1 minus xi, times the average of the two function values, which of course that gives me the area of my trapezoid. So it's the same as before, trapezoid rule. All I've done is show us how to derive it in a slightly different way, in a way that's going to be more similar to what we are going to do for Gauss Quadrature. All right, so nothing new, just a different approach to getting this. We can do the same thing for Simpson's rules. We can develop these equations. Just have to figure out how many constants we have, get the appropriate number of equations for those constants, solve the necessary nonlinear equations, get the C0 and C1, and we're done. And we'll just get different C0s and C1s for different methods. All right, that was lots of fun. But now we want to generalize this a bit. So we're going to set it up the same way. So the integral of f of x dx is still going to be C0 times f of xi plus 1 plus c, I guess it was xi, plus c1 times f of xi plus 1. So the same approximation, so the same functional form, but now not only will the c0 and c1 be unknown, but the x0 and x1 will also be unknown. So remember, I want to be able to move the point, so I have my sliver, but I want to be able to move my x0 and x1 points within that sliver so that I can get an even more accurate approximation for the area of that sliver. So now we need 4 equations because I have 4 unknowns, the 2 constants and the 2 Gauss points, x0 and x1. Now, the good thing about these Gauss points is once you get them, once you calculate them, you have them, they're the same. So for any situation, any f of x, you have, if you want 2 Gauss points, I'm going to derive them right now. If you want 3 Gauss points, 4 Gauss points, you can derive those, or you can get them from a book someplace, and they don't change. So you only have to calculate these once, derive them once, and then you just use them. That's the beauty of this basic approach. All right. So I'm going to take what we did for the trapezoid method as kind of a guide, but now I need to get 4 equations for my 4 unknowns. And I want to choose the I want to choose my f of x. I'm sorry, I want to choose the C0, C1, X1, C0, C1, X0, X1. I'm so excited about numerical integration. Yes, I'm a nerd. So I want to choose those points so that the I, the value of I that I get, is exact for all polynomials up to 3rd order. And that'll make sense in a second, because again, I need 4 equations. So I'm going to use constant, linear, quadratic, and cubic. So the first 4 orders of my polynomials to get my 4 equations for my 4 unknowns. Once again, we have the same form here. This is always the same for 2 points, 2 Gauss points. So C0 f of x0 plus C1 f of x1. And now I'm looking for both C0 and C1 and x0 and x1. Because I need 4 equations, I'm going to do the same thing we did for the trapezoid method, except I'm going to do it 4 times. I'm going to do it for f of x as a constant, f of x is linear, f of x is a quadratic, and f of x is a cubic. So here we go. F of x is a constant. So once again, integrate that with respect to x, that's x. Put in the limits of integration, which are now b minus a. So you notice the xi and xi plus 1 before defined my sliver. Now it's going to be a and b. A and b define the edges of my sliver. And now x0 and x1 are going to be 2 points that are inside a and b. They can be anywhere inside a and b. Okay, so integrate 1. I get x, put in the limits of integration, that's b minus a. On the right-hand side, I have the same thing as I had before for the trapezoid method. It was C0 f of x0 plus C1 f of x1, but f of x0 is 1, f of x1 is 1, f of anything is 1. So I have b minus a is C0 plus C1. Very similar to before. Then I do the same thing for f of x is equal to x. Integrate x, I get x squared over 2. Put in the limits of integration, I have 1/2 b squared minus a squared. Then on the right-hand side, again, same thing, but now f of x0 is x0 and f of x1 is x1. And so then that's what I get for my second equation. And I just keep doing this until I have enough equations. So that's 2, I need 2 more. So I do x squared. So integral of x squared is x cubed over 3. So it's 1/3 b cubed minus a cubed. And on the right-hand side, f of x0 is x0 squared. F of x1 is x1 squared. So there's my third equation. One more. So we do a cubic. F of x is x cubed. Integrate x cubed, that's x4 over 4. So it's a quarter b to the 4 minus a to the 4. And then my f of x0 is x0 cubed. F of x1 is x1 cubed. And there's my fourth equation. Is that clear what we're doing? So I'm hardwiring in, I'm determining these constants, C0, C1, Cx0, and x1. But I'm doing it exactly for constant functions, linear functions, quadratic functions, and cubic functions. That gives me my 4 equations for 4 unknowns. And then the answer that I get for those 4 constants will be the same no matter what. If I have up to 3rd order polynomials and I integrate them, I will get the exact answer. If it's anything higher than 3rd order, or if it's a non-polynomial function, well, of course, then it's only going to be approximate, but it should be a good approximation. Dr. Castle, do we guess 1x, x squared, x cubed? No, I'm specifying these. So I'm saying that I want to hardwire my Gauss Quadrature approach so that for constant, linear, quadratic, and cubic functions, I will get the exact solution. So that's my choice. I've made that decision. Now, I could have used, instead of x squared, I could have used 3x squared, but there's no point. It doesn't buy me anything. Okay, so now I have my 4 equations for 4 unknowns. Now let's take a look back at them. The first one's easy. It's just b minus a is c0 plus c1. This one's, okay, so I got squareds on the left, I got cubes now on the left, I got squareds on the right. So you can see the orders of the powers go up by 1 each time. So they're a little messy. They're 4 nonlinear equations for 4 unknowns. I could solve them in this form, but they're kind of messy. So what we're going to do is do a little change of variables just to simplify our lives. This doesn't add anything mathematically, nor does it take anything away mathematically. It just makes things work out a little bit cleaner when we solve these 4 equations for 4 unknowns. So what we're going to do is we're going to shift our x coordinate, which goes from a to b. We're going to shift it so that instead of little x, we have big X, which goes from -1 to 1. So I'll come back to the actual mapping that does that, the transformation that does that. But big X is -1 should correspond to little x is a, and big X is +1 will correspond to little x is b. So I'm literally just shifting and scaling so that whatever a and b are, they get shifted and scaled to go from -1 to 1. And that way it'll always be the same for every problem. No matter what the a and b are for the original problem, I'm going to shift them and scale them so that they go from -1 to 1. And then I can get my Gauss points and they will never change. So if I do, let's go back to 7,6 then, the actual transformation. So little x is 1/2 times the quantity by b minus a plus b minus a all times x. And if you think about what that does, so if I put in big X is -1, I will get that little x is a. If I put in that big X is +1, I'll get that little x is b. So it's just a linear transformation, nothing special about it, very intuitive. Again, just to shift and stretch or squash my a to b range so it goes from -1 to 1. That's all it's doing. So I found this guy on YouTube, forget his name, he's a dialect coach. And I've kind of been, this is a little bit embarrassing to say, think about what you've been binge watching lately. Well, I've been binge watching a dialect coach. It's fascinating. So he has different themes for each video. but a lot of them have to do with accents, like different parts of the US or even different parts of the world. And of course, they have names for all these things, you know, how the Boston accent is different than a New York accent. And of course, he can do all these accents perfectly, which is pretty amazing. And then he talks about like how the tongue, how we position the tongue for different sounds with different accents. I'm just fascinated by this. I don't think it's going to last very long, but that's my latest binge watching effort. Very interesting. Half the time I can't tell the difference. He'll say, and then, and a little different inflection, and they both sound the same to me, which I guess is why I'm an engineer. But can you imagine being a dialect coach? So training actors and actresses to speak authentically in a particular accent or language. It's pretty impressive, actually. Of course, I wouldn't know if it's right or wrong. I have a problem with distinguishing accents that are very close. And I think part of it is, so I spend a lot of time in England. I have spent a lot of time in England on sabbaticals and research collaborations and stuff. So the British accent versus the Scottish versus the Irish accents, I find it more difficult now than I used to distinguish between them. And part of the reason I think is because the English accent is very, very different in different parts of England. So if you go to London, you kind of get used to the official English accent, British accent, and then you go up north to Manchester or Newcastle or one of these places. It's amazing how hard it is to understand people. My most embarrassing moment was I was in Manchester, we would say, but they say Manchester. I was in a Tesco, which is a grocery store in Manchester. And when you check out, very similar to here, every time I went, they would ask, do you have a Tesco card? And I didn't, so I said no. So finally, like the 27th time, whatever number it was, I went through, got my stuff, go through the cashier line, and the cashier asked me, would you be willing to bag yourself? And of course, I couldn't understand a word she was saying. So I assumed she was asking me if I had a Tesco card. And I answered no. And she gives me this look like, who's this beep, 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 beep American who can come in here and make me bag his groceries for him? So I could tell I obviously had answered incorrectly. So I very politely and apologetically asked, so what did you ask? Yes, I'd be more than happy to bag my groceries. Very sorry. So anyway, it's fascinating stuff. Mostly because I really know nothing about it. Another thing that I find interesting is my wife is from Brooklyn, New York. She grew up in Brooklyn. She's kind of lost. Well, she has. You would never know it today. It's only when she's mad that the Brooklyn accent comes out. You know, the dogs and the coffee and all that kind of stuff. So you don't really hear it much today. But anyway, so she's from Brooklyn, which is a very distinct accent, which is different than New Jersey, which a lot of people think is the same, but it's very different. And upstate New York is very different. Anyway, but if you listen to a Brooklynite talk and you listen to someone talk with a British accent, they sound obviously completely different. You know, people talk with a British accent, they sound so intelligent, right? They could be a skinhead, completely uneducated, but they just sound so intelligent because they're talking with a British accent. You could be a PhD expert in XYZ, but if you talk with a Brooklyn accent, you just sound like average Joe person on the street. But if you listen to the sounds carefully, even though the overall accents sound very different, there are a lot of very similar sounds in British English and the Brooklyn accent, which of course there's a history for that, you know, where the people come from that now live, or the families that grew up live in Brooklyn. So anyway, it's kind of fascinating. The Midwest is pretty plain. So I'm from the East Coast. When I moved here, The only things that were a little different, like where Chicago, there's a little bit of awe. I would just say Chicago, but Chicago wouldn't say Chicago. And there's a few other little words like that that are a little bit different. The main thing is different words. Like everyone uses different words for soft drink. So I grew up saying soft drink. A lot of places will just say Coke. Generically, they'll just call it Coke. Some places call it pop, like in Western Pennsylvania. And here, what do we say here? I don't even remember. Soda? Yeah, pop or soda. So there's, people use different words for the same thing, but it's really very, Midwestern accent tends to be very generic. So if you, this is kind of cool. If you listen to a newscaster, you never think, no matter where you're from, you never hear an accent. It's amazing. So I can listen to a newscaster and they sound like they're talking just like I would. My wife, with her Brooklyn upbringing, can listen and she thinks they're talking directly to her. Southern accent. You could have a Southern accent, live in the South. You listen to the same newscaster and it sounds like you don't hear an accent. It's amazing. It's just a way to enunciate words. It's very difficult to learn. I just realized why these things got recommended to me. So this probably says more about me than the fact that I binge watch dialect coaches. So I think the reason why YouTube thought I might be interested in this is, has anybody heard of Charlie Behrens? He's a comedian in Wisconsin. Look him up, he's pretty funny. So he does a lot of stuff with Wisconsin accent and he really accentuates it. I mean, people in Wisconsin, no one talks like this. But he has this very distinct and very way overdone Midwestern accent. So he does all kinds of crazy stuff. He has his little Minute Talk Minute thing. He gives the local news. He talks about Midwest nice all the time, how Midwestern people are always overly nice, even when they shouldn't be, like on the roads. He bashes, of course, Chicago and Chicago Bears, because he's a Packers fan. But anyway, because a lot of it's based on accents, I think that's why YouTube made this connection between Charlie Behrens, the comedian from Wisconsin, and this dialect coach. So anyway, for once, Google figured out something I might like. They always get it wrong. Does it creep you guys out? Sorry to go on these rants. Does it creep you guys out when one day you're talking to a friend about, say, I don't know, some type of jewelry, and then within minutes, all of a sudden, every single online ad in your social media feeds are all about jewelry? Does that creep you guys out, or is that like, oh yeah, it's kind of cool because? Yeah. So this is a very generational thing. I find it, my generation finds it extremely creepy. Yeah, millennials are more likely to find it actually, a positive thing, but the problem is, yeah, there's certain situations where, sure, that's fine. If I really am looking for women's shoes, great, I have lots of ads for women's shoes, but most of the time I'm not looking for women's shoes, and so I don't want to see ads ad nauseum for women's shoes, but I don't get to pick, because, so my theory, and I think this is true, Facebook is by far the worst offender with this. So the biggest, or the most, well, the kind of the creepiest incident we had once, so a few years ago, we were flying someplace, don't remember where. My wife and I were not sitting next to each other, we had separate seats. She struck up a conversation with the woman sitting next to her, and they chatted pretty much the whole flight. The next day, on Facebook, she gets a friend recommendation for this woman. They never mentioned names, never obviously did anything on Facebook. Somehow, Facebook figured out that they were sitting next to each other for a couple hours on an airplane and apparently realized that they had a conversation and thought, well, gee, maybe they want to be Facebook friends. Mind blown emoji. That just, I mean, algorithmically, that's kind of cool from a, how do they do that kind of point of view, but from a, can I live my life without Big Brother looking over my shoulder point of view, that's really just maybe a little too much for me. And of course, the problem is that Facebook now, so I always forget, Instagram is Facebook, right? Google is YouTube. YouTube is Google. Instagram is Facebook. And I think, and WhatsApp, right, is also Facebook. Yeah, so they're all kind of now in these ecosystems, which of course use all your data. So I'm sure you're aware, maybe you're not, your IIT email is actually Gmail. So there are computers and servers and AI bots reading through all of our email all the time and guessing what you might want to spend your money on based on what's going on in your email. A little wiggy. For me, I was asking my friend if he wanted to go to, oh, now we're getting all the stories, to BWW, oh yeah, okay, Buffalo Wild Wings. And next time I opened Instagram, I had an ad, yeah. That happened when I worked over the summer, hated it. It too close, yep. They recommend on Facebook. And so, yeah. This is why Apple, Tim Cook and Zuckerberg, Facebook, why they get into these battles, because Facebook doesn't charge you for anything, right? I mean, everything, Facebook's free. So how do they make their money? They have to make their money. They have to what's called monetize. They have to monetize you as a user. By monetize, that means they have to get you to buy crud. So if they get you to buy crud, then they get a little cut from that. Advertising rates go up that they can charge their advertisers and all that. Apple doesn't make money off of you, the user, in that way. They make money by getting you to buy all their devices. Someday I'm gonna have a ring. I'm gonna wear an Apple ring. And it's gonna have all this biometric stuff, and it's gonna tell me, I'm gonna get an alert that my blood sugar is dropping and I should eat some candy. It's gonna get another alert that my blood sugar is spiking, so I need to chill out on the candy. Oh, it's gonna be huh? Yeah, there are some. I don't know how accurate they are. Yeah, they tried this for COVID too. So the current Apple Watches, they of course are tracking your pulse, estimating your calories burned based off that. You can check, you can do an ECG, and you can check your blood oxygen level, which is kind of cool. Like if you're going on a hike up a mountain, it's kind of interesting to see how much your blood oxygen level drops with altitude. It's pretty wild. So anyway, it's a very interesting debate. Here's a coding question for you. So why is Castle going off on all these tangents? Because I don't really have that much to cover. And because we don't have class for the next week, I don't want to start the next chapter until next Tuesday. So I'm stalling for time. But it's all very interesting, and I'll charge you extra because it goes beyond $350. So you'll get a bill in the mail. What profound thing was I going to say? Wow. Huh? Oh yeah, coding. So 10 years ago, Oracle, do you know what Oracle is famous for? What? Huh? That's right, they do. They sponsor a lot of big events, especially America's Cup sailing, because their former CEO is a big rich dude who loves to sail. The other thing the main thing they're known for is databases. So they've always had databases. They're used in companies all over the place. The other thing that they developed well, actually, no, I'm sorry. They didn't develop it. It was developed by Sun Microsystems, which no longer exists. It got bought by Oracle, is Java. So Java is a programming language. It's in the top 20 list. It's primarily used for writing code for browsers. So most code that runs in a browser is written in Java. So 10 years ago, Oracle sued Google because Google had taken several thousand lines of code from Java and used it in developing Android. Where have I heard of Android before? Well, it's the most commonly used mobile operating system in the world right now. Most phones, smartphones, most cars, the infotainment systems run on some form of Android. So they copied several thousand lines of code from Java and used it straight in Android. So this lawsuit, and this just shows how far behind the law is from what's actually going on in the tech industry, has been going on for 10 years. Finally, yesterday, the Supreme Court ruled that it's okay. So basically Oracle was saying, this is our code, we wrote the code, and you need to keep your hands off of it. It's copyrighted essentially. And Google said, no, it's open source. It's basically, anyone can get it and use it for whatever they want. They call it common use. And the Supreme Court ruled for Google. And this is a very, very interesting debate. Who owns your code? Because most code now is open source on some level. But everyone then massages it for their own use. So Mac OS and all of the iOSs and watchOS and stuff, they're all based on Unix. Unix is open source. You can go online, go on GitHub, and you can get the source code for Unix, and you can use it however you want. So that was the starting point for Android. That was the starting point for Mac OS, iOS, and so on. And for a lot of these infotainment systems and cars and everywhere else. So it is a very interesting debate. And so basically, it's just a Wild West now. It's a free-for-all. Whatever code you write, if it's available open source, anybody can use it for anything they want. Which from a technological development point of view is viewed as being a good thing. Why should Google have to rewrite those several thousand lines of code? Why not just use code that's already been written and tested, debugged, and so forth? But from the point of view of innovation and protecting your innovation, so what is a company like Uber? It's actually that's not an easy question to answer. What is a question like Uber? Is it a whole bunch of drivers in their cars? Or is it just an app on your phone? It started as an app on your phone. And all the drivers in their cars and the customers, those were all just people using the app. Is that code proprietary? Do they own it? Could Lyft lift that code? And could I lift that code, make a few little tweaks and changes to the app, the appearance of the app, and make it seem cooler, more modern, whatever, and generate a business off of that? Is that okay? So these are not easy questions to answer, is my point. It's very interesting debate. Okay, back to our regular schedule program. Facebook somehow knows every single one of my coworkers, despite me not even telling Facebook where I work. Oh, Facebook is the worst. All right. Maybe I don't like Facebook because I don't have friends. Maybe if I had friends, I'd have a different feeling about Facebook. Okay, where were we? Oh, yes. Oh, yes, yes, yes. I have all the friends I need. All right. So we shifted our little x to big X. Little x goes from A to B. Big X goes from -1 to 1. And again, that's just going to standardize the range over which we're doing our Gauss Quadrature. So now if you go back and look at those 4 equations for 4 unknowns and rewrite them using this transformation, these are those 4 equations. And you can see they're a little bit simplified. I mean, they're still, you know, this is still a third order polynomial on the left, but nevertheless, it simplifies the equations a little bit. Fine. So now we're going to use these, and all the details are in the notes. You can go through the algebra if you want, but I'm just going to quickly go through how we can solve these four equations for the four unknowns. Okay, it's not terribly astounding, but we'll just kind of walk through how we do that. Again, the details aren't super, super important. So we're going to solve these four equations. So start with 7.8. So 7.8 is this one right here. If you look at that, you can solve it for C1 and then substitute into 710. So solve this one for C1 and then substitute it into 710 for C1. So you basically have eliminated C1. Fine. If you do that, you'll get that x0 squared has to be equal to x1 squared. Now, it doesn't make any sense that x0 and x1 be the same. But remember, when you square, it could be positive or negative. So what we'll say is, we'll say that x0 is minus x1. I don't want them equal to each other because then my 2 points are on top of each other. That doesn't make any sense. So I want them to be different. The only way they can be different and satisfy this expression is if x0 is equal to minus x1. Okay, fine. If I take that result, substitute into 7.8, back here again, then I see that, okay, well then C0 and C1 have to be the same. All right, now we're getting somewhere. From 7.7, if C1 and C0 are the same, then they both have to be equal to 1 to add up to get 2. All right, I know C0 and C1 now, and I know x0 and x1 are just difference by sign. So if I substitute those results into 7.9, that's the only one we haven't used, this one right here. If I substitute the fact that C0 and C1 are the same and x0 is minus x1, then I can solve for x0 and x1. And I get that x0 is minus 1 over root 3 and x1 is 1 over root 3. And I gave you the decimal values if you'd like. So what's so special about these numbers? These are the values. So remember, my sliver goes from minus 1 to 1. But if I put my x0 point at minus 0.5773503 and my x1 point at plus 0.55 whatever, and I then integrate using those 2 points for x0 and x1, along with C0 and C1 both being 1, then I will get the exact value of the area under the curve if I have f of x be up to a third order polynomial. And that will also be, therefore, the best choice for any other function as well. We'll do an example in a moment. Okay, so I also have to transform the integral. The integral is written in terms of little x. So I need to write it in terms of big X. So dx, this is from here. If I differentiate that, I get the dx, little x, is 1/2 b minus a times d big X. So the integral of f little x d little x from a to b is the same as integrating f of big X d big X from minus 1 to 1, but I need a b minus a over 2 out front. So those are equivalent, just using different variables, little x and big X. But now I know the values of C0, C1, and big X0 and big X1. So I can approximate this integral in this form right here. So these, of course, are the Gauss points, plus and minus 1 over root 3. These are special points. They're special because of the properties that I've just outlined. And then again, multiply by b minus a over 2, and that will give me an approximation for the integral of f of x dx. All right, so I've said this several times, I won't repeat it again. But look, here's the key. I only need to actually do 2 function evaluations. Once I've done this whole derivation here and I get the Gauss points, I can throw away the derivation. I now know what the optimal Gauss points are. If I want to have 3 points instead of 2, or 27 points instead of 2, I can do this. I just need more equations to solve to get those points. Once I've solved for them, I know what they are. These are special points. So you'll find them in books. You'll find them online. Look in Wikipedia. They're all there. So 2 points, these are their optimal values. 3 points, you can find those online or in a book. 4 points, same thing. All right, so what happens then is, here's the point I was trying to make. All I actually have to do is evaluate f at these 2 special Gauss points and do this simple algebra, and I get an estimate for the interval I. That's it. Super simple. Very little actual calculation. And this is why it's so valuable in a context like a finite element method, where I have to do these integrations over and over and over and over and over again, many, many thousands or even millions of times. I want to make them as simple and as fast and efficient as possible. And so this is a great way to do that. Okay, if I want more points, I have more points. I can have as many as I want. So we did it with 2. I can have 3. I can have any number of Gauss points I want. I just need more equations to be able to solve for the points. Okay, so let's do an example. This is the example we've been doing now twice. So we did it for Trapezoid Method. We did it for Simpson's method. If you remember, the Trapezoid Method was about 5% off with 2 slivers, 3 points, 2 intervals. Simpson's rule was, if I remember right, was about 1% off. I think it was even less than 1% off. So that was an improvement. So let's solve the same problem, but now using 3 Gauss points. So 3 points again, as with the other 2 examples, but now using Gauss Quadrature. And let's see what happens. So it's the integral of sine x dx from 0 to pi over 2. And you'll see how easy this is. Once you have the Gauss points, you have the values of the Gauss points. This is a super simple calculation to actually carry out. All right, so let's do it. So I have my integral, 0 to pi over 2, sine of x dx. Fine. So f of x is sine x. I know what it is. I know what f of x is. So this is b minus a over 2, integral from -1 to 1 of sine half b plus a plus b minus a times x dx. And you'll notice I'm writing everything in terms of big X now. So we start with little x, the original problem. We write everything in terms of the new big X variable. This comes from right here, right there. Okay, so I went from this form in little x to this form in big X. That's all we did. And I'm recognizing again that the function f of x is actually this sign. Now, if I put in a and b, a is 0, b is pi over 2. So that gives me pi over 4 out front, integral from -1 to 1, sine of pi over 4 times the quantity 1 plus cap x, d cap x. So I just put in a is 0, b is pi over 2. All right. Now I need to get my Gauss points. So we actually have 3 now. So I got these from one of the textbooks that I recommended in the syllabus. Again, you'll find these all over the place. You can find them Wikipedia, wherever, it doesn't matter. But if you look in that textbook, it's table 7.1 or 9.1, depending on which version you use. And this is with n is equal to 3. So 3 points, left, right, center. And you just pull them out. So C0 is 0.555556. C1, 0.888889. And C2 is same as C0, 555556. And then the values of x, the Gauss points, x0, x1, and x2, again, all from this table. X1 turns out to be 0. X0 is minus 0.77459667, and X2 is 0.77459667. Yeah, that's a 4. Now, obviously, you're going to notice a pattern. When there are 2 of them, they're going to be plus and minus. So when there's an even number of them, there's going to be pairs, plus and minus pairs. When there's an odd number, you're still going to have plus and minus pairs, and then there'll be a 0 because it's an odd number. So these are the Gauss points. They're always between -1 and 1. Now it's 3 points between -1 and 1. And then these are the corresponding coefficients, C0, C1, C2, in here. C0, C1, and the next one would be C2. Once I have those, I just have to do the function evaluations at my Gauss points, plug and chug, and I'm good to go. So I'll do that next. All right. Now this is an approximation. It's an approximation because it's not a polynomial of 0, first, second, or third order. If it was one of those, you get the exact answer. If it's anything other than those, you'll get an approximation. So our I is approximated as C0, F evaluated at x0, plus C1, F of x1, plus C2, F of x2. So C0, there's a pi over 4. I'm going to put that out front. There's a pi over 4 in all of my F evaluations. So right here, I have this pi over 4 times sine of this. So I'm going to keep the pi over 4 out front, just to keep things a little tidy. So I have pi over 4 times C0 is 0.555556. Keep as many decimal places as you want. Times f of x0, so that's sine of pi over 4 times 1 minus 0.77459667. That's this first term, C0 times the function value, which is sine, evaluated at x0, which is, again, from these tables. This function is this function. That's my f of x. This is one of those where the theory behind it's a little like, I sort of get it, not sure. The actual doing it is super easy and straightforward. Now that's the first term. Then we do the same thing for the second and the third term. So the second term is plus 0.888889. That's C1 times f of x1, which is sine of pi over 4 times 1 plus 0. And then C2 times f of x2. C2 is, again, 0.555556 times f of x2 is sine of pi over 4, 1 plus 0.77459667. Remember what the exact solution is? It's 1. Even I can remember that. So the exact solution is 1 for this problem. And if you put those numbers into your fancy schmancy calculator, calculate with Python, MATLAB, whatever, you'll get an estimate for I, which is 1.00001. So I have a 0.001% error. So obviously this is extremely accurate, very accurate, with only 3 function evaluations. So that's awesome. So again, same problem, 3 slivers, well, 2 slivers, 3 points. Trapezoid rule was off by about 5%. Simpson's 1/3 rule, so that's a quadratic at the top, was off by about 1%. Gauss Quadrature, same number of points, but choosing them optimally, I only have a 0.001% error. Extremely good, extremely accurate. So that's very encouraging. Okay, we're almost done. So you can do this in MATLAB. There's a trapezoid method. It's called TrapZ. You just put in literally the X and Y vectors, which are the X and Y values of your data points, and it'll estimate the integral. There's also a quadrature type. It's called adaptive Simpson's rule. It sounds like it's more like Simpson's rule, but it's really a quadrature. It's actually called quad. You put in the function, put in the limits, X min and X max, and it will estimate the value of the integral. And this is all wrong. So I forgot to put in the Python stuff. So I'll add that in and I'll alert you to that. So I just copied and pasted obviously from the root finding and I forgot to update it. Oops. So I'll update that. All right, so we're done with numerical integration. You can now do problem set 6. It's posted on Blackboard. It'll be due Saturday by popular demand. So Saturday, that'll be the last problem set before the exam next Thursday. Here's my PhD comic. We haven't had one for a while. Student says to advisor, how do I know I didn't make a mistake in my computer code, Professor Smith? Professor Smith says, did you double check it? Yes. Triple check it? Yes. Quadruple check it? Yes. Did it confirm our hypothesis? Yes. Then stop checking it. So I've talked to you before about the confidence meter, right? So the student is expressing the fact that they have 0 confidence in the result. And Professor Smith is giving some clues as to ways that you can move the needle on your confidence meter. It's the only way to get it to 100% is if you know the solution. If you know the solution and your numerical approximation gives you that solution, woohoo, 100%. In real life, of course, that's not true, because if you know the solution, there's no point in doing it approximately and numerically. So these are ways to think about, kind of in cartoon fashion, but ways to think about how you move the confidence meter towards 100%. All right, the rest of the semester, starting next Tuesday, is going to be all about differential equations. This is where things really get fun. Whether you like differential equations or not, now we're going to solve them numerically. So not analytically, like you learned in DiffyQ, Math 252. So if you didn't like that, fine. We're going to show you how to solve them approximately, which is great because there are many, many more that we as engineers care about that we want to solve approximately, or we need to solve approximately because we can't solve them analytically than the ones you can solve analytically. So this is going to be a lot of fun. We'll spend the rest of the semester on it. It's kind of a beefy topic, but I'll walk us through it. And yeah, so integration is coming. Yes, so the second midterm will include integration, correct. So 5, 6, and 7, root finding, optimization, and numerical integration. Yep. Yep. No, you're going to have, so if you have, so the example we derived, we had 2 Gauss points and we needed 4 equations to get them because we also need to get the coefficients. So it's basically 2 times n. So if you want 27 Gauss points, then you need 27 times 4 equations. And the way you would do it is just more of the same. So you do constant, linear, quadratic, cubic, 4th order, 5th order, 6th order, 7th order, 8th order, and you just keep going until you have enough equations to get all of those values. Now, you're going to have 27 terms now instead of 2, right? So not only do you have more equations, each equation gets messier. So it gets very messy very quickly. And normally, so in a finite element method, your elements are small. So usually we use low order polynomials. We call them shape functions. We usually actually use linear or quadratic shape functions. And the reason why that's okay is because they're tiny. So if I want to do some huge FEM simulation, I might have tens of thousands or even hundreds of thousands, maybe even millions of elements. So each element is so small that I can do an approximation that's either a plane or a paraboloid. And then this is perfect because I only need 2 points. I don't need 27 because I'm going to get a really accurate approximation with only 2 points because there's so many small ones. So that's the trade-off. You can have bigger elements with more accurate shape functions, or you can have smaller elements and more of them, and then simpler shape functions. And normally the latter is the way to go. So you never need 27. Usually it's 2, 3, maybe 4. More often than not, it's 2. And that's all you need. And we just derived them. So you now know, the values. All right, anything else? Okay, so no class on Thursday. Study COVID. No, that's, we already went through that, right? So study something useful like 350 material, get ready for the exam next week. I think there's only one other COVID study day, and I think it's on a Friday, so it doesn't affect this class. I think it's later in April, and if I remember right, it's on a Friday. All right, so I'll see you. Have a good rest of the week, and see you on Tuesday.